In this video, we're still talking about the histogram mean standard deviation system, but now we're talking about center, spread, and outliers. So let's go back to our yak cheese question. Here we have our 18 yaks. All right, we have our histogram that we did in the last video. All right, we already know that it's mound-shaped symmetric. That was the shape we did in the last video. Now the center, which actually we also did in the last video, is the mean. And here's the formula for it. Again, capital sigma and x means the sum of all the x's, or sum of your data, over the number of numbers. Right? That's a fancy way of talking about your mean. You add them up. You divide by the number of numbers, and you get the average, which we got the last time, which is graphically in the middle. If this was a balance, right, and this was the fulcrum, then this is the balance point. Right? That's what the geometric meaning of mean is. But now, let's talk about spread. And what does spread really mean? Really, it's going after, on average, about how far from the data from the center is the data. Is a lot of the data far away, or is most of the data close to the center? That's really what spread is talking about. We need a little bit more space here because this is going to take some calculating. Right? If we want to know the distance or difference the data is from the mean, right, then we ask for this first one, 37, how far from the center is that one? Right? Well, how far is it? That's difference. And that's a subtraction. So we take our data minus the mean, and it's negative because, of course, 37 is a little to the left of 37.81. Left means negative direction, so it kind of makes sense. So you always do data minus mean, and you get your distance, and the sign indicates direction, either left or right. So if we want to do that or write that symbolically, it'll look something like this. We have our data x minus x bar is the symbol used for mean, right? Which I did write over here. You can see that. X bar is mean, and to be a little bit more specific, it's sample mean. We're not going to talk about population mean. We'll talk about that in a little bit, but just know that x bar is sample mean. And it's also called the deviation. Right? So this data deviates to the left a distance of 0.81. Right? We can then do it for the second data point, and then of course we can do it for all of them. And we get all of the deviations, and we can add them all together, and we get 0.02. Kind of interesting, actually, because that's almost zero. If we look at the diagram and graphically, what does that actually mean? If our average deviation is 0, we're saying that on average, the data isn't any distance away from the center. Well, does that make sense? I mean, we have a lot of data, some data, which we know is some distance away. So what's going on here? Well, the pluses and minuses, well, if it's symmetric, then the pluses above and the minuses to the left kind of balance each other out, and when you combine them all, it approximately equals 0. So that's kind of a problem. So the solution is, as I've written up here, is to square it. Because what does squaring do? It makes what's negative positive. Right? And what's positive positive. So we'll make it all positive. So that's exactly what we can do. Here I've shown everyone is raised to the 2, it's squared, and that converts. I haven't squared these yet. I'll do that right now. Bam. So here they all are, and you can see they're all nicely positive. And so it's probably not going to be 0 anymore. And we add them together, and we get this nice, really big number, 6,310 and some odd, which, again, if you think about what spread is supposed to measure, does it make sense that on average the data is a distance of over 6,000 on this number line? No. Now we're at the other extreme. From the center, like 6,000 is like way off. Like, what's going on? Well, we are trying to find have we averaged the deviations? No, we've just added them up. That's not averaging. We have to divide by the number of deviations, which is 18 in this case, and we get this 350. Now, the symbol that is used for standard deviation is the lowercase Greek letter sigma. So the question is sigma in this case 350.6? Well, let's do that reality check thing. Does that make sense? On average, is the data 350 units away from the mean? No, it's still way off the screen. That still doesn't make sense. What's going on? Well, squaring does two things. It makes everything positive, but it also makes everything big. So it's now way too big. It's not the normal scale on our graph. So that's not the average distance from the center. We have to undo what we did before. We squared it. So at the end, we have to square root it, and we get 18.72, which that kind of makes a little bit more sense. And as a matter of fact, if we actually talk about that distance, and there is really the equation. Right? We went through the calculations sort of by hand. Right? Here's the equation. Let's pull it apart. You can see here's the individual deviations. Right? We're squaring them. So that's these numbers. This capital sigma is saying add them all up, which is this down here, 6,310. We're averaging it, so we're dividing by the number of numbers. There's the 18. And then in the end, we're square rooting it. And we get our 18.72. And oftentimes what we use is this abbreviation for standard deviation. Now I need to get a little space, move things up. Let's move that up, because it gets a little bit more complicated. Because there's not one measure of spread for the histogram system, but there are two. Sigma is standard deviation, S is sample standard deviation. Now, these are 18 yaks. Does this represent every yak everywhere, or even all the yaks in a particular region? No, there's only 18 yaks. This is clearly a sample of yaks. Right? So whenever you have a sample, which is not all of whatever you're talking about, you're going to use sample standard deviation. And the only difference is in this denominator. Instead of a normal averaging, you're actually going to do n minus 1 in your division. So this would actually look something like this. We're still going to add up all of our deviations, but instead of this 18, we're going to divide by 1 minus, or 18 minus 1, and we end up with a slightly larger number with an abbreviation of sample standard deviation. The question is, well, we have two measures. We have one data set. What's the right one? Well, is this all of the yaks or just a sample of the yaks? Well, it's just a sample. So we should use S, or sample standard deviation. Well, let's figure out what this is really telling us. How do we use sample standard deviation, which will be the same as population standard deviation, which is what sigma is often referred to as, is population standard deviation. So when you know all of the measurements. So if we go 19.27 above our mean, right, we get to this point. If we go 19.27 below, we get to this point. And that we can continue, and need a lot more space. We could keep going, and we could go not just one sample standard deviation, we could go 2 and 3. And we can get all these sort of boundaries for different distances from the center. And and if we wanted to use, looks like I have 18 point, this is the old one. I'll go back one. It should be 19.27 because sample standard deviation. Looks like that might be a typo actually. But what's important here is that we are dividing this into regions. And the regions have meaning. Right? If you are within one sample standard deviation to both sides, plus or minus 1, that's actually typical variation. That's the measurements that you would expect to find. If you are up to 2 sample standard deviations away, between 1 and 2, right, those are starting to get kind of unusual. You wouldn't expect to get those so often, but not too bad. And the farther we get from the mean, the more unusual it gets. And this is kind of a rare case, right? Happens occasionally, but we're getting more and more unusual. And if you get more than 3 standard deviations, they're totally weird. Like, these are really unexpected measurements and bizarre. You start questioning their validity, as a matter of fact. And this is actually what outliers are. That's the definition of outliers in the histogram system, is 3 or more standard deviations from the mean. So let's look at a new example. What we're going to do is use our yaks from what we did before, so same data. And we're going to say, well, these yaks came from the Nubra Valley up near Leh in Ladakh. And then maybe we go over to Mongolia, and we find 18 yaks over there. It didn't have to be 18. I mean, it could have been 20 or 50, actually. It still would be a sample. But, happened to be the same, 18. That's fine. All right? And I plug this into L1 and this into L3. I could actually show you. I do have here. You can see I've plugged those into L1 and L3. And if we move forward, right here we have the mean calculation for L1 of the Nubra Valley, and there's the calculation. Now, I'm using this function sum. I should probably show you where that is on the calculator. So what I'm going to do is second quit to get to my home screen. And over here on the stat button, you can see that the second function is list. So these are all the list functions. I go second list. We have names, ops, math. If we go over to math, we can come down over here to 5, which is sum. So I can hit 5. And I can go L1, so it's going to sum up L1, and we get this sum of all that data. We can do the same thing for L2. If you were paying attention, if we go back to our list and go over to math, you'll actually notice, look, number 3. That says mean. If we go mean of L1, right, 37.811, we get the mean. We can check ourselves. So it depends on what the question is. If there's a quiz or a test or something like that, and I ask, please show how to calculate the mean, then I want to see this. But if the question isn't show how to calculate mean, then you can use this function, and that's fine. So now let's clear that. Let's continue over here. So if we want to calculate the sample standard deviation, we can do our squared deviations and get all of those. Again, it might be useful to actually show you how to do that on your calculator. So we go back into our editing, and I'm going to go up, and what I want to do is put this equation into L2. Now, a common mistake is to start typing now. We can't do that. We have to go up so that the header is highlighted. And now what we're going to do is enter in an equation, and I can go parentheses, and I'm going to go L1, second L1, minus 37.81, and parentheses, and hit the squared button. And there I've entered a formula, and all I have to do is hit enter, and it's going to completely fill L2. So I can get all those values all with one equation, which is super helpful, especially if you have not 18, but 50 of these things. It's way easier. So you can see those where all those numbers came from. Now, let's continue. We can run through our sample standard deviation. What we're going to do is sum up L2. We're going to add all of those. We get, this is something we did just a moment ago. Divide by 17, we get our 19.27. Right? Now we do the same thing over here. Right? We get actually a much smaller sample standard deviation. Right? Notice that the means are nearly identical. Right? The differences are pretty far out in the decimals. But the sample standard deviations are quite different. Right? So that tells us something very important about the data. Right? If we look at our distributions, if we make the histograms, right, they look like this. And you can actually see visually that this one is just a lot more, narrow. That distance is less than that distance. So that's what this smaller standard deviation is telling you. There's really less variation that you would expect in Mongolia for whatever the reason. Now let's talk about this example. So same example, but we need to ask some new questions. So the new question would be, what would be your expectation for finding a Nubra Valley yak that produced 75 kilograms of cheese in a year? Well, expectation, what's that about? Well, if we do our mean, which is x bar for Nubra Valley, x bar n, right? And we go 1 sample standard deviation, 2 sample standard deviations, and 3 sample standard deviations above, and the same thing, 1, 2, 3 sample standard deviations below. We get something like this. Well, where's 75? Well, and those define our typical, unusual, rare outlier regions. Well, 75 is in the unusual. Well, that answers our question, right? It would be unusual to find a Nubra Valley yak that would produce 75 kilograms of cheese in 1 year. Another question would be, what would be your expectation for finding a Mongolian yak that produced 75 kilograms of cheese per year? We have a different spread. If we do our Mongolian sample mean and do our 1, 2, 3 sample standard deviations, now using this 9.64, we get different boundaries, and 75 turns out to be way out here as an outlier. So it would be so radically unexpected to get 75 that I would question the validity of the measurement. Now, questioning the validity of the measurement does not mean rejecting it. Right? It means I need to investigate it and say, did someone go out and mismeasure? Was there miscommunication? Was there a typo as they entered the data into the computer? Anything could happen to produce such a bizarre outcome or data measurement. So that hopefully clearly shows you how you use the sample standard deviation. And of course, if you actually have sigma, your population standard deviation, you would do the exact same thing. It would still create the typical, unusual, rare, and outlying regions, and you use it in the exact same way.